Hi everyone, in this video we are going to address old Regents questions related to the mole, so moles, and balancing chemical equations. Number 1. The mole of which substance contains a total of 6.2 times 10 to the 23rd atoms? Well, let's take a look. Well, to begin with, let's remember that just like 1 dozen equals 12, 1 mole is equal to 6.02 times 10 to the 23rd. Now that is a way of measuring a quantity, not a quality of anything, just a quantity similar to a dozen. So if I were to inspect these choices, it brings me straight to choice A, because 1 lithium, that would be only 1 mole of lithium would be represented by choice A. If we were to take a look at choice B, we would notice that we have 1 mole of nitrogen with 3 moles of hydrogen for a total of 4 moles. Choice C has 2 moles of oxygen, while choice D has 1 mole of carbon with 2 moles of oxygen. So that again confirms our answer is choice A. Number 2, if 6.02 times 10 to the 23rd molecules of N2 react according to the equation 1 mole of N2 combining with 3 moles of H2 yields 2 moles of ammonia, the total number of molecules of ammonia produced is, well, it's not 6.02, it is 6.02 double, because we have 2 moles of it. So which one of these values is double that of 6.02 times 10 to the 23rd? That is choice D. Number 3. Given the balanced equation representing a reaction, we have a hydrogen ion aqueous, so it is dissolved in water. Excuse me. We have a hydroxide ion aqueous, again dissolved in water, combining to yield H2O as a liquid and giving off energy. So if it's giving off energy, we know this is an exothermic reaction. Just thought I'd throw that in. In this reaction, there is a conservation of mass only, mass and charge only, charge and energy only, or charge, energy, and mass. Let's dissect this. Let's first look at, grab a pen here, the idea of conservation of mass. So here we have 1 hydrogen, 2 hydrogens on the reactant side, 2 hydrogens on the product side. We have conservation of mass by way of hydrogens. 1 oxygen as a reactant, 1 oxygen as a product. We do have conservation of mass, so that works, and that works. Alright, so choice C is eliminated. Let's now take a look at charge. A +1 charge here, reactant side, with a -1 on the reactant side. Well, that would become, if combined, a net charge of 0 from the reactant side. And if we notice here, there is no mention of a charge, which implies that it is also a neutral charge. So we do have conservation of charge. So conservation of charge is mentioned here and here. So choice A and C are eliminated. Now, do we have conservation of energy? And because it is identified that the energy is leaving, it is exothermic, it implies that there was extra energy here. So if the energy is mentioned, it's to balance that out, to suggest that it is also conserved. The answer is D. Number 4. A balanced equation representing a chemical reaction can be written using chemical formulas and mass numbers, chemical formulas and coefficients, first ionization energies and mass numbers, or first ionization energies and coefficients. Let me first tell you, it has nothing to do with writing first ionization energies. So is it the chemical formulas with the mass number or chemical formulas with the coefficients? And that's exactly what it is. B, the coefficient, which is the number that can lie before a reactant or a product to modify its quantity. So the coefficient would be that big number that goes before the formula, and the formula itself is necessary for writing a balanced chemical equation. Question 5. Base your answer to the following question on the information below. Here we have a 1 gram strip of zinc is reacted with hydrochloric acid in a test tube. The unbalanced equation is below represents the reaction. So we have zinc as a solid combining with HCl aqueous, so that's hydrochloric acid, yielding hydrogen gas and zinc chloride. So it's asking us to balance the equation for the reaction of zinc and hydrochloric acid using the smallest whole number coefficients. Now to do this, we are going to need to account for the masses, and to account for the masses, we just account for the atoms. On the left side, reactant side, how many zincs do we have, how many hydrogens, and how many chlorines, and on the right, the same thing. Okay. So, on the left, how many zincs do we have present? It shows just 1. How many hydrogens? 1 and 1 chlorine as well. So 1 and 1. On the right side, how many zincs? 1 zinc, 2 hydrogens, and 2 chlorines. So 1 zinc, 2, and 2. Now what is the easiest way to balance both of these out? In other words, how do we find out what the ratio between the reactants and products should be? So the zincs balance 1 to 1. We're having a problem here. So let's just say I add 2 hydrochloric acids, 2 HCl's for every 1 zinc. Let's see what happens. Now that we've doubled that, this becomes 2. And what happens to the chlorine? That also becomes 2. Inspect once again, and we have 1 zinc on both sides, 2 hydrogens on both sides, and 2 chlorines on both sides, representing a conservation of mass. And right then and there, that balanced the equation. Number 6. Which equation shows conservation of mass and charge? So, in order to identify conservation of mass, we must identify how many of each element are on the reactant and product side, and they must balance. Let's look for that first. Here we have 1 nitrogen on the reactant side, 1 nitrogen on the product side, 4 hydrogens total on the reactant side, and total only 3 hydrogens on the product side. We already know A cannot be the choice. For B, 2 magnesiums on the reactant side, only 1 magnesium on the product side. It is also eliminated. For C, we have a total on the reactant side of 3 hydrogens. 3 moles of hydrogens, 2 here, 1 here. On the product side, only 2 moles of hydrogen. It is already eliminated itself. So it's looking like D would be great, but let's confirm. 1 mole of copper, 1 mole of copper. 2 moles of silver, 2 moles of silver. Now this says plus 1. This says plus 2. So does that conserve charge? It actually does, because if you notice here, this coefficient, we have 2 silvers. So we have 1 silver carrying a plus 1 charge and another silver carrying a plus 1 charge for a total on the reactant side of 2 plus, which in fact does conserve the charge because we have a 2 plus on the product side. So it is choice D. Number 7. Given the balanced equation with an unknown compound represented by X, it's asking which compound is represented by X. So we do know that because of conservation of charge, the atoms that are represented by the reactant side must be the same as on the product side. So let's take a look at this. On our reactant side, we have 6 moles of carbon total, 12 moles of hydrogen, and another 6 moles of oxygen. By the way, that's glucose. On the right side, we have, in the square, we have 2 moles of carbon and 4 moles total of oxygen here. So let's rewrite this by eliminating this. So we said 2 moles of carbon, no hydrogens being represented, and how many oxygens? It was 4. So we are looking for a balance of 4 carbons, still 12 hydrogens, and 2 oxygens. Now, that might equal X, but X has a 2 in front of it. So we have to, in a sense, divide this by 2. So we are going to be looking for C2H6O. Now, is that one of our choices? Ooh, this is tricky because it does not represent it in this formula. So, do we have 2 carbons here? No. 2 carbons here? Absolutely. Do we have 6 hydrogens? 3, 5, 6 moles of hydrogen. Do we have 1 oxygen? Absolutely. Therein lies our answer, choice C. Number 8. Given the unbalanced equation, here we have iron 3 oxide combining with carbon monoxide to yield free iron and carbon dioxide. The task: when the equation is correctly balanced using the smallest whole number coefficients, what is the coefficient assigned to carbon monoxide? Now, the way to address these questions is to balance the number of moles of each particular element on both sides of the equation. So on the left side, we have irons, oxygens, and carbons. On the right side, we have irons, oxygens, and carbons. Now, how many of each? On the left, we have 2 moles of iron, a combined 4 moles of oxygen, and 1 mole of carbon. On the right, we have 1 mole of iron, 2 moles of oxygen, and 1 mole of carbon. Now, what I'm going to do next is I am going to inspect. My irons do not balance, but I do notice that this is free iron, and in order to balance that, it's easy to do at the end. I could just always bump this number up without affecting any others. My oxygens do not balance, but my carbons do. So let's increase the number of oxygens by putting a 2 here. Now that bumps this number up to 4, and that balances nicely, but inadvertently it doubled the number of carbons. So in order to affect that, I now need to roll back here so that my carbons increase. But inadvertently, that made my total number of oxygens 5. Now let me try this instead. Let me put a 3 here. And if I put a 3 here, I will end up with 3 carbons. Now I'm only doing this by inspection, trial and error. Okay, and on the right side I would have 6 moles of oxygen. Now in order to balance that out, I would then need to put a 3 here to give me 3 carbons, and that would give me a total of 6 moles of oxygen on the left. Now we only care about this coefficient because that's what the question said, and the answer is 3. Just as a side note, let's not forget about the irons. In order to balance the irons, somehow we have to drive this number up. So if we put a 2 here, this would become 2 moles of iron on the product side and the reactant side. So that would also balance.